In this part of the lesson, we're taking a look at solution curves, a way to visualize what particular solutions to differential equations look like. The general solution of a first-order differential equation can be represented graphically with a family of curves that we're calling solution curves. If you look at this one that's over here on the left, its differential equation is y is equal to 3x squared minus 1. If I take the antiderivative of that, I know it should be some sort of cubic equation, and that's what we're seeing here, a whole bunch of cubic equations, and you can see that they're just vertical translations, and the one that's locked in here at the initial condition 2, 4 is the one that's highlighted there in black. Look over here on the right-hand side, the differential equation is xy prime plus y is equal to 0. This one would be a little bit tougher to solve, and notice this time, however, we don't have vertical translations for our constant of integration. Instead, if we choose a different value of c, what it's going to do is vertically stretch or shrink this graph. Okay, so solutions to differential equations. Again, they're generally pretty tough to solve, but these two methods are going to give us a way to visualize and approximate what they look like. Okay, so this first one is an example of a slope field. This one is both an AB topic and BC topic. So you can see that these tiny little segments that are in this little picture here, these represent the slope at that particular point. And kind of like you've got river currents, if I stuck a little boat on that little river current, it would follow through one of these little paths determined by one of those colored graphs. Over here on the right-hand side, this is what Euler's method looks like, and this is a BC only topic. This is what our second objective is all about. And as I said, this one is very similar to course correcting. The solution, the actual solution is the graph that's in pink. Our approximated solution is the course corrected one that's right down there at the bottom in blue. You can see it's kind of accurate for a little bit and it gets a little bit further off. Okay, so I'm going to have to course correct and make it a little bit steeper so it can mimic the actual shape of that graph. Okay, so slope fields. I'm going to start off by taking a look at a differential equation we haven't seen before. This says y prime is equal to a function of x and y. Right over here at the top of the screen, you can see y prime is equal to x plus y. It has x's and y's in it. And a differential equation is basically giving you the slope at each point in the plane, right? Y prime is the slope of y, the original equation. It gives you the slope at every point in the coordinate plane. And what we're going to do is we're going to visualize this with something that's called a slope field or a direction field. And in this particular kind of graph, you draw a tiny little segment that represents the slope of a line at that particular point. It's as if we really zoomed in on that particular point. It's like local linearity, and it would look like a tiny picture of a line. So let's look at a couple of points here. So here's the origin. I would take 0, 0 and plug it into this differential equation right here. I'd have 0 plus 0 is equal to 0. The slope at that particular point should be 0. So I'm going to draw myself a tiny little horizontal segment at the origin. Let's pick another one. This one is at 1, 0. So again, I plug it into the differential equation, and I would have 1 plus 0 is 1. I have a slope of 1. If I zoomed in at that point on my actual function, my solution, it would look like this tiny little line right here. Let's look at another one here. This one's at 1, 1. 1 plus 1 is 2, so I should have a slope of 2. It's a little bit steeper than the one that's down below it. And let's do maybe one more. This one's at 0, 1. 0 plus 1 is 1. It has a slope of 1. It should be parallel to this other one that has a slope of 1. It looks like that. And then here's a whole bunch more of it. This is what a slope field looks like. And the AP Calculus exam might ask you to generate a slope field by hand. And usually it's not more than about 6 to 10, maybe 12 points, but not too many. And they're always usually pretty easy to plot. Okay, so basically this works on the principle of local linearity. It's that idea that for differential equations, or differential functions, I should say, that when you zoom in on them, they start to take on the aspect of looking like a line at that particular point, right? Over some small interval. So let's see if we can make ourselves just a tiny one from scratch. This one's just asking for 3 points. And here's my differential equation. It is y prime is equal to x minus y. It's very similar to the other one, but now we're subtracting our x and y coordinate to get the slope at that particular point. So the first one we're going to look at is negative 1, comma 1. So I'd plug these into my differential equation. Negative 1 minus 1 is a negative 2. So at negative 1, 1, at that particular point, I need to have a slope of negative 2. One way to visualize this is at that particular point, go down to over 1 and draw yourself kind of a little line, a little ghost image of a line, and then you just want that small little portion there. Okay, at 0, comma 1. So that's our next point. 0 minus 1 is negative 1, so this time I want a slope of negative 1. Again, I could go down 1, right 1, and visualize what that line is supposed to look like, and then just draw myself a little tiny line. This one should be less steep than the other one, which was a negative 2. Okay, and then finally we're going to look at 1, comma 1. So if I plug 1, comma 1 in there, 1 minus 1 is 0, so I should have a little horizontal line segment right there. And what they look for, if you have a question like this on your AP exam, they look for horizontal and vertical slopes. They look for positive versus negative, and then relative steepness. If you have a slope of 1 versus a slope of 2, is that slope steeper than the other one? And they're not that picky about it because it's really hard whenever you don't have little tools and stuff, you don't have a ruler or anything like that, you just have your pencil and you're drawing yourself a little line. So there is a little bit of leeway there, but just make sure that you're doing positive versus negative slopes, horizontal slopes versus vertical slopes, and then the relative steepness. Keep that in mind as well. All right, let's take a look at some of these where we have slope fields already generated for us, and we're trying to match them up. We've got 3 slope fields and our 3 differential equations to try to match them with. Y prime is equal to x plus y prime is equal to just x, and y prime is equal to y. So I'd like for you to pause the video right now and see if you can visualize which one of these differential equations goes with which slope field. All right, so let's see if you got them right. So the first one, y prime plus, oh, we're not going to go in that order. The very first one, A, y prime is equal to x, is A. B is the y prime is equal to x plus y, and the C should be the y prime is equal to y. So let's see why that is what it is, and what are the things that you can look for whenever you're trying to match up slope fields. This usually comes into play in a multiple choice kind of situation where they would do something very similar. They might give us a slope field and then ask us which one of these differential equations goes with it, or kind of the reverse of that. It gives us a differential equation and then gives us 4 slope fields to try to match it up with. Okay, so on this first one, y prime is equal to x, what you should notice is that each one of the columns has the exact same slope as the x value there. That means that the differential equation does not depend on y. It has no effect. Okay, so let's look at the second one that's over there. This one this time is all the horizontal lines have the same slope as the y coordinate. This means that it's not dependent upon the x coordinate. And one other thing that you can look for, I would look in the first quadrant. Notice that on this, the one that's over here, y prime is equal to x, in the first quadrant, everything's positive. If everything's positive in the first quadrant, there's probably not going to be a negative sign in there. There would need to be a negative sign in there in order to make the slopes go in the opposite direction. Okay, so let's look at some multiple choice kind of slope field questions here. Which differential equation is most likely associated with this slope field? So we got 4 to choose from. Y prime is equal to 0.5xy, x squared over y, 0.5x squared, and x over y. So pause the video and see if you can make your way through this particular differential equation, seeing which one of these matches up with that slope field. All right, which one did you get? Let me actually come back over here to Notability so I can write on the screen and stuff. Okay, so notice that just like in this example here with the vertical columns having the same slope, the same thing is happening right here. I need to change this to green so everything matches up. Like everything here is the same, everything here is the same. All these vertical columns are the same, which means that our slope does not depend upon y. Anything that has a y in it, I'm going to cross out, which leaves only one answer, which is C. And this one has a bit of a typo in it. The original one is supposed to have a squared in it. And just think about, I want to say, let's see if it actually has that on here on the slideshow. It did, okay. All right. If you were to solve this thing backwards, you take its antiderivative, it should be a cubic equation, and you can see a cubic kind of function playing out in that slope field right there. All right, let's take a look at the next one. Which of the following differential equations could have the slope field shown in the figure? Okay, so we've got 4 to choose from once again, x squared plus y squared, y over x, negative y, and negative x over y. So, just like we did on the previous one, just pause the video for a sec and see if you can work through this on your own. All right, again, I want to be able to write on the screen, so I'm going to come over here. Now, this one here in particular, this A, is very deceiving because x squared plus y squared, it makes a circle, and I might start to think, hey, isn't that what this is? Well, that's what the equation, the original solution curve is supposed to look like, but not the slopes. Matter of fact, that's the first one that I'm going to cross out, is that one. And now the next thing that I'm going to look at is just this first quadrant over here. Notice that everything in this first quadrant has a negative slope. Since it has a negative slope, that's going to eliminate boop, B. And now we just have 2 choices. Is it negative y or is it negative x over y? Well, if it was negative y, then that means that columns have to have the exact same slope. Let's take a look at one of these columns. Just pick one of these columns. Do these have the same slope? Nope, because these slopes depend on both x coordinate and the y coordinate, so our differential equation needs to be d. dy dx is equal to negative x over y. All right, so we're going to stop this video for right now, and then we're going to take a look at how we could actually make our own little slope fields.